Okay, as I said, this lesson we're going to get into today gets a little bit deep. By deep here, I mean that it can be quite complicated. There's a lot going on. We're looking today at what's called a simple harmonic oscillator, but we're going to be looking at specifically the spring system, where we have a mass oscillating on a spring, and more specifically, it's going to be for a horizontal spring. So we're going to describe the energy transformations that occur when a mass is in an oscillation at the end of a spring, and we're going to solve problems involving conservation of mechanical energy for the oscillation. To begin with, when you have a mass oscillating on the end of a horizontal spring, the force that the spring exerts on the mass changes. It's not the same force all the time. And the reason for that, I can't set up a horizontal oscillating spring very well, but let's just imagine that the mass is where this piece of tape is on this spring. And what's happening is it's doing that. Okay? It's on a frictionless surface, and this end is fixed, and this is bouncing back and forth. Okay? When the mass is in this position, the spring is stretched quite a lot, which means it applies a great force to the mass. When the spring is stretched here, it is not stretched as much, so the spring does not apply as great a force. So all I'm saying to begin with is when you have a mass oscillating on a spring, the force that the spring is exerting on the mass depends on where the mass is. The more the spring is stretched or compressed, we'll talk about the compression in a bit, away from the equilibrium position, the greater the force on the mass. This is AKA, also known as, this is Hooke's law. Right? Hooke's law says the force that the spring exerts on the mass is negative kx, and I'm going to be including vectors for some of this discussion today. So x is how far away the mass is from the equilibrium position. It's called the displacement. If it's stretched more, then negative k times x will give you a larger amount of force acting on the mass. Oh, well, could have saved myself a little bit of writing there. This is what's known as Hooke's law. So as a warm-up, and apparently I didn't save this. As a warm-up for an ideal spring where there are no frictional forces present, if that has a mass oscillating on a horizontal surface with that spring, show that the magnitude of the net force is always the magnitude of the restoring force. Man, there's a lot to unpack with that statement. But what I'm going to do is I'm going to draw a system, and you can sketch it as well, where we have a vertical surface that we're going to connect the spring to. And we have a horizontal surface that the mass is going to be sliding back and forth along. So now we can draw in the spring. You don't have to be an artist here. Just draw in a few loops, and then we can connect this to a mass. And it's in oscillation. You have to visualize that I've maybe pulled it out to some point and I've let it go, and it's going to be springing back and forth. You also have to understand, and I'm going to have to use one of these springs that are stretched out to help you visualize what's going on here. You have to imagine that it's this type of spring, which can be stretched and then it goes back to its equilibrium position, or it can be squished and then it goes back to its equilibrium position. So it's not the type of spring that you've used in your Hooke's Law lab where all of the coils were touching each other. It's something that can do this. Okay. It's not very practical because we have so many ideals here, like there's no friction, which is ridiculous, but it will help you understand what's going on in terms of energy. So I pull this back and I let it go, and it maybe goes back and forth from this point to this point. It just oscillates. And how quickly it oscillates depends on the mass, it depends on the spring constant. But what we are asked to do is explain why the net force is the force that the spring exerts on the mass. So let's imagine right now that this mass has been pulled to the right, away from where it would normally be. So if I just attach it and I leave it alone, the mass would be sitting right around this location, but I've pulled it to the right. That means right now that the spring is exerting a force that way, back towards the equilibrium position. So this is the force that the spring exerts. Are there any other forces acting on the mass? Nate? Gravity. There's a gravitational force. I don't know how big it is because I don't know what the mass is, but there's a gravitational force. Any other forces? Nate? There's the normal force. And what's the relationship, Nate, between the normal force and the gravitational force in this situation? Equal but opposite. Perfect. Well said. Most people will just say, well, they have to be the same. They have to be equal in magnitude but opposite in direction. So this is the normal force. Are there any other forces acting on the mass? No, that's it. So if I said to you, what is the net force? F net equals the sum of the forces. But if you add those three forces together, you get the force that the spring is exerting on the mass. This is why, even though we can't set up in a high school physics lab a mass oscillating on a horizontal spring, it's easier to analyze. Because when I had yesterday, and I took the springs down, but when I had the vertical spring and the mass bouncing up and down, the net force acting on the mass at any point in time involves the force that the spring is exerting and the force of gravity. And that gets too complicated to analyze in terms of energy. It gets very easy to analyze in terms of period. So this is equal to F sub s, the force that the spring acts on the mass with. Why is the acceleration of the mass not constant? This is really interesting. Those kinematics formulas, everybody. If I pull up your formula sheet here. These kinematics formulas, like A equals delta V over delta T, or D equals VIT plus 1/2 AT squared. Those 5 kinematics formulas are only valid for uniform acceleration. They're only valid if the acceleration of the object is always the same. But what I'm telling you in the second part of this warm-up for B is that the acceleration is not constant for a mass oscillating on a spring, so we can't use those formulas to do any kind of analysis at all. But my question to you is, why is the acceleration not the same everywhere? Or better yet, why is the acceleration changing depending on where the mass is?
Because it changes direction that it goes in.
That's true, so that's one of the answers. Sometimes the acceleration will be in a positive direction, sometimes it will be in a negative direction. Does the value of the acceleration ever change? Well, this is interesting, and I'm going to use what Aoki said as kind of a springboard to talk about this. If the acceleration at some point is 3 meters per second squared to the right, and then it changes to 3 meters per second squared to the left, the numerical value of the acceleration changes from positive 3 to negative 3. You can't have something change in nature in terms of motion until you get to physics 30, where we talk about such a possibility. You can't have a mass on a spring having an acceleration of 3 meters per second in one direction and then immediately having 3 meters per second in the other. The 3 meters per second in the one direction has to decrease to 0 and then increase in the opposite direction. But is there another way to explain why the acceleration will have a value that's different depending on where the mass is? Nate?
Because of the spring, like if it's pushed more together or if it's stretched further out.
So you're exactly right, but we can boil it down to something even more significant. Because it's stretched more or less, the force will be more or less, right? So when the spring is stretched a lot, Hooke's law says that the magnitude of the spring's force will be greater if it's stretched more. But the spring's force is the net force, and the net force is ma. So because the force acting on the mass changes, the acceleration will change because acceleration is determined by the net force. So if you have a changing position, then you will produce a changing spring force, which will produce a changing net force. I'm not sure why I didn't just use delta to begin with, which will produce a changing acceleration. These things are all tied together. Stretching more, as Nate says, gives you a greater spring force. But since that spring force is the net force, it gives you a bigger net force. But since the net force determines the acceleration, it gives you a bigger acceleration. All right. What two types of energy are present in the mass spring system? So the mass is oscillating back and forth. What's one type of energy that the mass would have at some point in time? It would have spring potential energy. And it would have spring potential energy whenever it is not at the equilibrium position. So spring potential energy and, do you know the other one, Aoki? You mean gravitational? No. Well, I mean, it may, because you may be doing this experiment on the 12th floor of a building, but it's not going uphill or downhill anywhere, so we can just say that at whatever level that is, there's no gravitational potential energy. Zahara? Kinetic. It has kinetic energy. Another reason why, although it's very easy for me to set up the hanging spring that we saw yesterday and put it in oscillation, it's very easy to see why we don't want to analyze that situation, because that situation would have spring potential energy, gravitational potential energy, and kinetic energy. It gets too complicated. And those are the only two types of energy that are present. D, if there are no frictional forces present, what stays the same, even though as it oscillates back and forth horizontally, the force on the mass changes? I hope it's clear the speed of the mass is going to change. the acceleration will change. The spring potential energy will change because the more it's stretched, the more potential energy is there. The kinetic energy will change because when it slows down as it gets to the furthest point, just before it stops, its kinetic energy will change because it's slowing down. All those things change, but something stays the same. That's true. The mass of the object does stay the same. The spring constant stays the same. I'm looking for some bigger picture here, though. Zahara?
The energy in the system because of the friction?
What kind of energy you're right, but what do we call that type of energy? Mechanical. The mechanical energy remains constant. And what that means is that mechanical energy is conserved. And I'm going to be using the pendulum here to draw a comparison between what we're going to talk about today and something you're familiar with, which is a pendulum. I just have to shorten the pendulum so that we can take a look at it swinging. So if I have the pendulum swinging here, and there's no friction. Now we know that's a bit of a lie. There's a little bit of friction at the top, at the pivot point. At this point right now, at the highest point, all of the mechanical energy is kinetic. Potential. Would you agree? It's all gravitational potential energy when it stops here. And as it falls, that potential energy decreases until at the bottom all of the energy is kinetic. You still with me? And as it rises, that kinetic changes back to potential. And what I can say, as long as I use this point as a reference point, so the lowest point has no potential energy, what I can say is this. My hand will be the highest point. I'll try not to move my hand. The potential energy it has here is the same as the kinetic energy it has here. Would you agree? But I can also say the potential energy it has here is the same as the potential plus the kinetic it has here. Because if it's all potential at the highest point and it's all kinetic at the lowest, that means in between it has a mixture of the two. And we've talked about this before, and what's happening is, at the top it's all potential and zero kinetic, and as it falls, that happens, and then as it rises, that happens, and it continues to oscillate back and forth. So if I have a mass oscillating on a spring, and I'm going to have to ask you to use your imagination here. Again, I have to teach you something that I can't show you. I can show you a vertical spring. I can't show you an oscillating horizontal spring. And I have a spring in which I push the mass on the spring to this point. Give me a second to create this. I push the mass into this point, and then I let it go, and as a result, it starts moving this way. So I push it into, I got to change the order of these, I guess. I push it into this point, I let it go, it comes back to here. Are you with me? And then it keeps going. I just want to look at my spacing here. And then it keeps going. I have one too many. Yep. To there. Are you with me? So what happens is, I push it in, I let it go, it springs back to here, but it continues moving to there, and this is where it stops. And then it goes back to the middle, and then it goes to there, and it stops, and then it goes back to the middle, and it goes to there. You get in my drift here, in my little cheap animation? This point is the equilibrium position. Just like the point that the pendulum is at right now is the equilibrium position. And when this pendulum is in motion, the displacement on one side of the equilibrium position is always matched by the displacement on the other side. And when the mass of the pendulum is at its maximum displacement, which is here, all of the energy is potential. But when the pendulum is at the position that's the equilibrium position, which is right here, at this point, it's all kinetic. I'm okay. Thank you for your concern. So this is like the lowest point in the pendulum. At this point, and we're going to formalize this on some diagrams in a second, but at this point, what we're talking about here is maximum speed. It's moving as fast as possible. Whereas at this point, it's stopped. And at this point, it's stopped. But at these points where it's stopped, there's maximum potential energy. And what we are asked to do on the next page shows snapshots in time of a mass spring system with the mass at various displacements away from the equilibrium position. The mass is pulled to the position shown in the first diagram and oscillates back and forth with no friction present. On each diagram, we have to label all the information. What is the kinetic energy? What is the potential energy? What is the velocity? What is the acceleration? What is the force? What is the displacement? All of these things have to be measured. So if you take a look, this is the equilibrium position, diagram 2. Unlike the one I did, what somebody has done is they have pulled the mass to the right. So they are pulling the mass and they're holding it right at this point, and they're going to let it go. So what happens is the mass is going to go from this position to this position where it's maximum compression, then it's going to go back. The mass is going to be doing that. Are you with me on what those diagrams show? Okay. So before we label anything, I pull the mass out, that's diagram 1. I let it go. I take a picture of it as it passes the equilibrium position. And then it continues past the equilibrium position, and I take a picture of it at this point where it stops. And then it's going to be pushed back to the equilibrium position in diagram 4, returning to 5, which is where it started in diagram 1, and it's just going to keep going. Are you with me? Okay. So let's talk about the speed first. I think the speed is pretty easy. The velocity here in the first diagram is 0. And you know what? Since we're primarily going to be interested in energy transformations, let's not worry about vectors. Energy is a scalar. So the speed here is 0. What can you tell me if anything, about the speed of the mass when it's at the position shown in number 2? You're not going to be able to tell me how fast it's moving, but you can tell me something about its speed. What can you tell me about the speed of a pendulum when this pendulum passes the lowest point? What do we know about the speed? It really was coming at me fast. What do you know about the speed of the pendulum at the lowest point? You got to be able to tell me something about the speed at the lowest point. Aoki? Sorry, a little louder. It's the fastest. That's all I'm getting at. The speed at the equilibrium position will have a maximum value. And as it goes from the position shown in diagram 1 to the position shown in diagram 2, the speed will go from 0 to some maximum value, just like the speed of the pendulum goes from 0 at its maximum displacement to a maximum value for the speed at the lowest point. Once it passes that point and moves towards the point that's shown in number 3, it's going to start slowing down. And it's at this point, when it stops, that the speed will be 0 again. And then when it gets to the middle, you will have a maximum speed again. And then, of course, it's going to stop. Because diagram 5 is the same as diagram 1. We've gone a complete cycle back and forth one time. What about the force? So is there a force acting on the mass, a spring force? Is there a spring force acting on the mass in diagram 1? Yep, definitely. Because it's stretched away from the equilibrium position. Hooke's law says F equals kx. So the force acting on the mass will be in this direction, and the force will be a max. The reason is the force is all tied up in this equation. I'm going to neglect the negative for this explanation. The force is all tied up in F equals kx. And since that point in diagram 1 is where the mass stops, that means it's where it's got a biggest displacement. So the force will be biggest. What will the force be here? Well, 0. And this is the thing that you're really going to have to wrap your heads around. The fact that in the middle, it's moving as fast as possible, but at that point, the net force acting on it is 0. There's no force acting on it right there. Well, there's a force of gravity down and a normal force up, but they cancel. When it gets to this point, you're going to have a maximum force again. It's just that it will be back towards the equilibrium position. The force is always trying to restore the mass to the original equilibrium position. When it gets back to the equilibrium position on its way to the right, since the displacement away from the equilibrium position is 0, there will be no force, and then it repeats. Right? We're back to the beginning, so now we have this force in that direction that's as large as possible. What about the acceleration? Well, the acceleration at this point will have a maximum value. And I know that that's very counterintuitive to most people, because you look at that and you say, well, wait a minute, it's not moving there. How is the acceleration the greatest? Acceleration is how quickly or rapidly the velocity is changing. And because the force acting on it at that point is the greatest, it's going to go from moving in one direction to the right with a certain speed to another direction to the left with a different speed in a very, very short period of time, so the acceleration is large. If you have ever been on a ride at Edmonton Exhibition, Klondike Days, Calgary Stampede, any of those things, and the ride involves taking you in a car of some kind where you change direction very rapidly. There's a ride called the Zipper. I don't know if you guys are familiar with this. No, the Twister, where you're in cars that move around like this, but they also move back and forth. And it's where you change direction that you feel the most influence on your body. It's where the acceleration is the greatest. It isn't that you're moving very fast at that point, it's that your velocity is changing very rapidly. Over here, even though you're moving as fast as possible in the middle, you're not accelerating at all in the middle, because the net force is zero. You're moving really, really fast, you're just not changing your velocity at that instant. So what we're doing is we're equating acceleration to the force, which is the net force, which is the spring force. By the time it gets to the other side, you have a maximum acceleration again. By the time you get back to the middle, you have zero acceleration. And then, of course, when you get back to here, you have a maximum acceleration. We have a couple more things to put. Amplitude. You need to understand that this is the amplitude. The amplitude is a very specific displacement. It's the displacement when you're furthest away from the equilibrium position. If you look at what we said yesterday, I don't even know if we talked about amplitude yesterday, but we did talk about it during Hooke's law. The amplitude is the biggest displacement away from the equilibrium position. So it's at the amplitude there. It's also at the amplitude here. And it's also at the amplitude here. The only other thing we have to add is the types of energy. Well, if it's not moving here, then at this state, the kinetic energy is zero, and the potential energy, that spring potential, is a max. Again, it's just like a pendulum, except the directions of the motion in a pendulum actually change because it's attached to a string. And this is moving in two dimensions. It's moving left and right and up and down. But at the amplitude, which is where my finger is, at that instant when it stops, turns out the acceleration will be a maximum, but I don't want to worry about that. Turns out the restoring force will be a maximum. I'm interested in energy. No kinetic energy here, maximum potential energy here, maximum displacement here. At this point, the kinetic energy is a max, and the potential energy, that's spring potential energy, is zero. And I think you could fill in the blanks for the other ones. Look, I'm not so sure. I want to make sure you understand something. We're not doing this so you can study these diagrams. We're doing this so that you understand what's happening as a mass moves horizontally back and forth. You're thinking this through, because it's going to lead to something that we are going to have to apply in a minute or two. At this point up here, well, it has zero speed, so the kinetic energy is back to nothing. The elastic or spring potential energy is a maximum. It reverses here. Now we have a maximum kinetic. And a zero elastic potential. And then when it gets to where it started, same thing as it had to begin with. The kinetic energy is zero, and the spring potential energy is a max. Are you able to follow all that? Okay. We've left out a significant part of understanding what's going on. We have talked, I'm going to use the pendulum as an analogy. We have talked about everything that happens here, everything that exists about the pendulum at the highest point, everything that exists at that highest point, and everything that exists halfway in between at the bottom. But what we haven't done is talked about, and this is where it started, we haven't talked about what's going on here. In between zero displacement and the amplitude. And I didn't want to add that extra diagram in here because I think it would get too confusing. So let's take a look at warm-up 3. What about when it's not at the maximum displacement and when it's not at the equilibrium position? What's going on there? Well, I can just do a rough sketch here. And rather than drawing the box and the spring, what I want you to do is put 3 lines, one in the center, one to the left, and one here, that represent x equals 0, x equals positive a, and x equals negative a. I guess since I'm using positive and negative, x is a vector in this context. Are you with me what those 3 positions mean? So we've talked about the fact that at a and negative a, there's no kinetic energy and it's all spring potential energy. We've talked about the fact that at 0, there's no spring potential energy and it's all kinetic. But in between, so here, where x is between a and 0, it's not stopped and it's not in the middle moving as fast as possible, then what's important is there is spring potential and kinetic energy. I almost said spring potential and spring kinetic. There's no such thing as spring kinetic. Kinetic is kinetic. So the energy forms that are there are a sum of potential and kinetic. I don't know that I want to clutter up your workspace here with everything else. The speed of the mass there is some intermediate speed. It's not 0 and it's not the maximum speed. It's something in between. The force acting on the mass there is not 0 and it's not the maximum force. It's someplace in between. Okay? But the point I want to get at is the following. If the mass is somewhere in between, this is the mechanical energy. If the mass is here, then the mechanical energy is only kinetic. If the mass is here, or on the other side at A, then the energy is strictly spring or elastic potential energy. Are you still with me? Because I know this is, as I said, heavy. It's deep. We go all the way back to the beginning where we said since there's no friction, mechanical energy is conserved, which means any three of these highlighted energies can be set equal to each other. I can say that the maximum potential energy is equal to the maximum kinetic. I can say the maximum potential energy is equal to the sum of potential and kinetic somewhere else. Or I could say the sum of kinetic and potential somewhere else is equal to the maximum kinetic. If mechanical energy is conserved, all three of those things are always the same. And now we're going to put that into practice. So we're looking at example 1. A 50-gram mass is oscillating on the end of a horizontal spring, and it reaches a maximum speed of 15 centimeters per second. What's the maximum displacement? So this 15 meters per second, I don't think you, or centimeters per second, I don't think you want to add anything to your diagram in warm-up 3. I'm just talking about if that's the maximum speed, that's the speed it has in the middle. What kind of energy does it have in the middle? Only kinetic. So what we're going to do here is identify this with EK max. And then it says, what is the maximum displacement? Well, we can identify this with EP max. Because when the displacement's as big as possible, the potential energy is as big as possible. And when the potential energy is as big as possible, there's no kinetic. These two energies have to be equal. This is just like, and I know you might get tired of seeing the pendulum, but or maybe not, this is just like saying that the potential energy this pendulum has right here is equal to the kinetic energy it has right there at the bottom, right? This is easy. The physics is what's tough. EK max equals EP max. What does that mean? It means 1/2 mv squared equals 1/2 kx squared. And we can even cancel the halves. But we have to use standard units. You cannot use grams, you cannot use centimeters. So I'm going to go ahead and cancel the halves. The mass is 0.05 kilograms. V is 0.15. We have to remember to square it. K is 25 newtons per meter. And we're going to solve for x, which will be the maximum displacement. What are we going to have? 0.05 multiplied by 0.15 quantity squared, well, squared, divided by 25 gives me 4.5 times 10 to the negative 5 meters. Very, very tiny maximum displacement. That tells me, by the way, did I calculate something wrong?
Isn't x squared?
Did I not? Oh, and then square root. Thank you. I still need to take the square root. Thank you, Declan. I was, to be honest, a little puzzled why that displacement was that small. I knew it was going to be small, but not that small. When I take the square root, I get 0.0067, or 6.7 times 10 to the negative 3 meters. Is that the right number now? Okay. By the way, that's 6.7 millimeters, about 67% of a centimeter. This spring is a very, very strong spring. It's tossing this mass back and forth very rapidly over a short distance. If you knew how to calculate the period, you would discover that the period is very small. Okay. What is the maximum acceleration? Well, acceleration is related to net force, but the net force is the spring force, and sometimes it helps to include the negative, and sometimes it's just not worth it. I hope it's clear that if you want the maximum acceleration, you need to be talking about the maximum force, and the way you get the maximum force is to have the maximum displacement, which we've found, right? This is the amplitude or the maximum displacement. If you put the maximum displacement in here, then you're going to get the maximum force coming out. If you put that maximum force in here, you're going to get the maximum acceleration coming out. So you have two options for you to complete this question. You can put this into your spring force formula to calculate the force and then put it here to calculate the acceleration, or you could be a little crafty about it and just say ma equals kx. So if we just take k times that maximum displacement divided by the mass, we would get the maximum acceleration. 25 times my answer divided by the mass in kilograms, which is 0.05. 50 divided, it was 50 grams, wasn't it? Okay. Divided by 1,000 is 0.05, gives me 3.4 meters per second squared. Any questions with number one, example one? All right, two, and I think this is the only other example, am I right? Okay, good. A mass oscillating on a horizontal spring has a maximum speed of 25 centimeters per second. Just a second here then. If V max is 0.25 meters per second, if I calculate the kinetic energy with that, if I go EK equals 1/2 times the mass times this number squared, which I understand we can't do because I don't know the mass. That's not my point. If I did that, why would that number that I get be the total mechanical energy in the system? In other words, why is EK max? Let's face it, if I use the maximum speed, I'll get the maximum kinetic energy. Why is this the total mechanical energy in the system?
Is it because it's at the equilibrium point?
Right, because that's at the equilibrium point, which means there's no potential energy. If it's moving as fast as possible, that means it's in the middle, where x is 0 and there's no spring potential energy. That's the total energy in the system. And then it says it has a maximum displacement of 13 centimeters. If I were to calculate EP max using that maximum displacement, why is that also the total mechanical energy in the system? Aoki. Right, because at the maximum displacement, just like the pendulum, it stops, and at that maximum displacement, if it stops, it has no motion, and if it has no motion, it has no kinetic energy, which means all of the mechanical is tied up temporarily in potential. So we're just going to set these two things equal to each other again. You're going to have 1/2 mv squared equals 1/2 kx squared, and we know all of the numbers except for m. I'm a little disorganized in how I wrote all this down, so I'm just going to continue it in the next line. If I cancel the halves, I have the mass, which we don't know, times the 0.25 squared equals k, which we do know, times the maximum displacement 0.13 squared. We can figure out what the mass is. (40 multiplied by 0.13 squared divided by 0.25 squared gives me a totally unrealistic mass. I'm going to have to redo these questions. 10.8 kilograms. Do you get 10.8? Okay. So the mass here is 10.8 kilograms. And then for part B, what is the speed when the displacement is 6? Okay, just a second. The maximum displacement is 13 centimeters. When the displacement is 6, is all of the energy kinetic? No, because it's not in the middle. When the displacement is 6, is all of the potential energy the mechanical energy? No, it's a mixture. But we can still say EP max equals the sum of those two energies. So this is at 13 centimeters. This is at 6 centimeters. But we're still saying mechanical energy is conserved. This is 1/2 kx squared. This is 1/2 mv squared. This is 1/2 kx squared. Can I cancel the halves? What do you think? Can I cancel the halves? Yeah, there's a half in everything. I can multiply the whole equation by 2. A question for you. What's the difference between the x on the left and the x on the right? Zahara?
On the left it's 13, on the right it's 6.
Right, they're just different numbers. So this would be 40 times the 0.13 squared equals the mass. Well, we found the mass, didn't we? It was 10.8. It's your call as to whether you want to carry a whole bunch of decimals. I don't really care. And then times v squared, well, we don't know that. We want to find that, plus 40 times 0.06 squared. Okay, we're just about home. I just want everybody to look up here for a second. I don't want you to get lost in the math. This is just some number. Don't worry about what it is, but just think about it. It's just some number. This is some number. This is some number times v squared. So how would you get v by itself? You'd have to take a minus b divided by c and then take the square root. I don't think you want to overcomplicate things and start rearranging this. You can do it on your calculator. Take 40 times 0.13 squared, subtract 40 times 0.06 squared equals, divided by 10.8 equals, take the square root. Anybody else get about 0.22? All right. So it's about 22 centimeters per second, 0.22 meters per second. You know, in the end, you can see what the assignment is there. In the end, what you're doing is you're saying, this. You're saying that 1/2 kx squared at A is equal to 1/2 mv squared at 0, and it's equal to 1/2 kx squared plus 1/2 mv squared anywhere else. It's conservation of mechanical energy. I think on this handout, I'm not sure you have to do every single question, and I've said this before, and I know it might not be a lot of help, but you don't have to do every question, but you have to know how to do every question. So, if you feel you're getting into the swing of things, you might skip a question or two. But don't look at a question and go, wow, that one's different. I think I'll skip that one. If it's different, try it. All right, get to work, please. You've got about 15 minutes, well, between 10 and 15 minutes left. Tomorrow, we're going to get more time to practice with this. I think what I would like to do tomorrow is start talking about the period of a spring. And we'll probably do a little bit of lab work tomorrow where you have springs and you have to determine a spring constant from a period. Not a spring constant by measuring forces, but a spring constant by measuring a period of oscillation.